Hi, welcome to Module 4 of Lecture 9. In this module, we're going to discuss expectations of random variables, expected utility, and the uniform distribution. A lot of the stuff we're going to talk about in this module you've done already, so it shouldn't be much of a stretch from what you've done before. Recall that the expected value of a random variable, we stick an x here just to be sure we're talking about x, if it's discrete, is equal to the sum over all values you might see times xi times the PMF here, where the PMF represents the probability of drawing any particular value xi. For a continuous variable, we're going to make the same transformation we've been making, going from a sum to an integral. So now we want to integrate the PDF multiplied by the variable x over all possible values that x can take. All possible values for a continuous variable in one dimension now go from negative infinity to infinity. So for a continuous variable, it's going to be the integral from negative infinity to infinity to cover all possible values, x, f of x, dx, where the dx represents the variable of integration. And that's it. The transformation between a discrete case and a continuous case is just that straightforward. There's nothing fancy about it. You just move from the sum to the integral. All the meaning is the same in terms of trying to take x and basically do a weighted average over all values that x can take, where the weighting is the probability of drawing a particular x in the case of a discrete variable, or the relative likelihood of drawing a particular x in the case of a continuous variable. The only difference you're going to find is when you deal with these probabilities, they'll naturally end up summing to 1 in a sense. I shouldn't say naturally. They're still, as you saw for the Poisson distribution, there can be normalization factors like e to the negative mu in front that make sure they sum to 1. The same thing would be true for the continuous case. They're in some senses even more important for the continuous case because unlike the discrete case, when the probabilities actually are individually equal to, so where the PMF values are individually equal to the probability of drawing that xi, that value xi, in the case of the continuous distribution, the values of the PDF are just their relative likelihoods. So it's especially important to make sure that you have a normalization constant to make sure that this thing over here equals 1. So the chance of drawing some value of x is going to be equal to 1 and not more than 1, which is often likely the case when you have a PDF that can be greater than 1 by itself, right? So I can't add, I have to be very careful when I add that I'm making sure that the overall integral is normalized to 1 so that the chance of being somewhere in space is going to be equal to 1. Assuming this is true, which is going to be true for every PDF you deal with, by definition, although it's not a PDF, then this thing over here would be an appropriate weighting each value of x by the relative likelihood of drawing that value of x, integrating over all possible x in a continuous space, and that will produce the expected value of the variable x. Expected utility is the same exact thing. We write it like this, but it's really just the expected value of the function of x, which is going to be equal to the same thing, but replacing x with u of x. And that is expected utility. Again, nothing different, nothing fancy, nothing conceptually different from before, from the sum. It just moves a sum to an integral, and that's it. And that's the expected utility for the continuous random variable. Now there is one difference. When you sum over a PMF, a utility function, you can be pretty general in how you're going to deal with the utility function. So for instance, I can specify that the chance of the first one is going to be 1/6, and the chance the second one's going to be 1/3, and the chance of the third one's going to be 1/3 as well, and so on. And I could have 100 of these things and get them smaller and smaller, or make them randomly, distributed. So there's some 1/6 and some 1/100ths and so on. As long as I add to 1, I'm fine, right? And I can, because it's discrete, I can actually write out all different probabilities of drawing each particular value, and I'll be fine if they add to 1. That gives me a lot of flexibility in terms of being able to manage these sums. However, for the case of the continuous case, if you recall, integrals are harder than sums in that way, And integrating something like this can be pretty tricky. So for instance, if this thing is a normal distribution, which you'll see later in this lecture, it's going to have a PDF that looks like this, if it's a standard normal. Which is fine and all, except you're going to have a hard time integrating this thing out unless u happens to be some multiple of x. So if you have a nice multiple of x out there, then you can use substitution, integration by substitution, to integrate that function. And if you don't remember how to do this, you can go back to the lecture on integration by substitution, and an example very similar to this is in there. But if you have something more complicated, like say the square root of x, you're out of luck. So it can get pretty tricky to deal with integrals of just generic PDFs, even though there might be some good substantive reason to use them. So instead, what you see most often when you deal with utility functions and expected utility is a particular kind of PDF, known as the uniform distribution. The uniform distribution, so if a variable x is distributed uniformly, this little curly thing means distributed as. You have a u, and you give it some bounds, say a to b. This notation means the random variable x, and that should be a capital, just to be clear, it's a capital X. The random variable x is distributed uniformly on the region a to b. What does that mean? Well, that means there's an equal chance of drawing any value from a to b. That's easy to see in the discrete case. If x were a discrete random variable, right, then you might have, for instance, say a equals 1 and b equals 6. It's a discrete random variable. Then you might have the probability that the probability of drawing 1 equals 1 sixth, and so on. The probability of drawing 6 is 1/6. That would be a uniform discrete distribution, a discrete uniform distribution, because the chance of drawing every one of the discrete set of values is equal. That's what you have if you flip a coin. There's 2 values, heads and tails. If you roll a die, there's 6 values, 1 through 6, and so on. These are all discrete uniform random distributions. They come up sometimes in political science, but less frequently, because oftentimes you can just assign probabilities to events and don't have to bother with invoking distributions at all. In contrast, for continuous distributions, you can't do that. So you want to use the uniform distribution. However, it's actually pretty easy to deal with because we're not actually concerned with with absolute probabilities, but rather with relative likelihoods. So if we want to make the chance of drawing every particular value in some range the same, we can just start by assigning it to be 1. If every point is 1, then they all have the same chance of being drawn. That's pretty easy. Now, if you're watching the screen right now, you might wonder, well, you drew a 1 and then you drew a bracket, and what are you doing? 2 things. One is not enough. Why is 1 not enough? Well, because it's only 1 between a and b. So we have to add an if here. This is going to be a piecewise function. It's equal to 1 if x is in a to b, and it's equal to 0 otherwise. This ensures that the distribution has an equal value anywhere between a and b, but has no chance of drawing anything outside of a and b. So uniform distribution looks kind of like this. If this is a and this is b, over here this is 1 and this is 0, there's no chance of drawing anything outside a and b. They're not in the support of a distribution. Anywhere from a to b, there's the same chance. So that's part of it. The other part is that 1 is not necessarily sufficient for us. So consider the fact that all distributions must satisfy this constraint, that if you sum them all, the chance of being anywhere has to equal 1. As you can kind of guess, integrating 1 over an entire range is not guaranteed to give you 1. So let's figure out what that actually is. Now note that the actual function f is 0 anywhere outside of a and b. So we're going to split up the integral to A, and there's going to be 0 there. And then we're going to split up, so we're just adding zeros, they stay 0. And then we're going to have the middle part that goes from A to B, and there's going to be 1 there. And then we're going to have the end part, which is going to go to infinity from B, and that's again 0. We'll get rid of these dudes, and we're left with this thing over here. So that's the first step. I should have left more room here. So right in the corner over here in blue so you can see it. Now we need the integral from A to B of just dx. Well, this is the same thing as the integral from A to B of x to the 0 dx. The power rule says that that's going to be the integral of x to the 0 is x to the 1, or x. So this is going to equal x evaluated at a and b by the fundamental theorem of calculus. Again, if this stuff is not familiar, go back to the lecture on integration. And that's going to be equal to b minus a. That's not 1, right? So we need this integral to be 1, and it turns out the integral is actually b minus a. So to make it 1, we're going to have to divide by b minus a. And there you go. That tells us the actual value of the integral of the distribution is going to be 1 over b minus a times 1, but so it's 1 over b minus a if x is between a and b, and 0 otherwise. And that gives us the continuous uniform distribution. Where we use that? Well, think back to our example we had before when we talked in the previous lecture when we discussed expected utility. Near the end of the lecture. At the time, we said we were interested in the probability of winning some election. And I'll go through really quickly what the setting was again to remind you, because I'm sure you remember at this point, unless you're watching this really fast in a row. So the game was this. You had two parties, A and B, and they had to locate on this line from 0 to 1. This is a policy space line, and anywhere they locate is the platform they're putting forth in the election, and then they were required to enact that platform should they win the election. So they're going to pick policies PA and PB, pick platforms on this line. Each individual party had a policy preference. They wanted to have a particular policy enacted. That's what they cared about. Party A wanted to get as close to 0 as possible, because the policy that maximizes the utility of negative x squared is 0. It's the biggest one. B wants to get as close as possible to 1. So there's their utility function, because 1 makes that the biggest possible. The highest value is 0, and 1 makes that close to 0 as possible. What makes it 0? So that's what B wants. And the trick was that the median voter, who is the important voter here, because the median voter's position, whoever's closest to the median voter is going to win a majority of the electorate, and thereby win the election, assuming majority rule. The median is distributed uniformly on 0 to 1. Now, before we did this example in the last lecture, you didn't know what that meant. We just kind of talked through it real fast, did a little hand waving. But here we actually can do it formally because we know what that means now. Now, let's say you have A here and B locates here. Then the midpoint of this thing is PA plus PB over 2. That's the midpoint of these 2 points. And we know that whenever the median ends up happening to be over here, then A wins. And if it's over to the right of the midpoint, B wins. Well, how do we know what the chances are of locating between 0 and that midpoint? That's the CDF, because that chance is the same as the chance of locating less than the midpoint. That's when you get to the midpoint, that's when you win, and this is the probability that you win. Probability that A wins. Now that we know the uniform distribution, we can solve this. I can write this out. A CDF is from negative infinity to the midpoint here. And I keep swapping superscripts and subscripts. Doesn't matter here, but I should be more careful. Of the distribution of M, dm. Now what's that? I should have left myself more room. It's 0 outside of the domain 0 to 1, outside of the support 0 to 1. So it's going to be from 0 to the midpoint now. And the distribution is 1 over b minus a, right? That's what f is in between 0 and 1. But b is 1 and a is 0, so b minus a is 1, so it's 1 over 1, so just 1. So it can't get any easier, and you get this. Therefore, you're integrating that over this. It's the same as one we just did in the previous slide, which gives you m evaluated at pa plus pb over 2 to 0. The 0 is 0, so the answer is just the midpoint. So if the m is distributed uniformly, the probability of winning for party A is exactly equal to the midpoint of the policies of A and B. And with that, you can then go through and maximize A's utility conditioned on B's action, and maximize B's utility conditioned on A's action, and then go through and simultaneously solve the two equations, and that gives you the solution for the equilibrium of this particular model. This kind of thing you see in game theory. In game theory class, we do a simplified version in the book, so you can check that out. But the important point for this particular module in this lecture is that we can compute the chance of winning, which is the total probability of m's being to the left of the midpoint, by using the CDF and the uniform distribution. And the other point is that you can see from this example why the uniform distribution is used so often. Because it doesn't add any m's or x's or whatever, it adds no variables to your actual utility function, it's a whole lot easier to deal with expected utility. Right? So one more quick example. If your utility were x squared, right, if that your utility function, and it was distributed in some fashion, and x was distributed in some fashion, we're trying to figure out what the expected utility is. As we saw in the example of the normal distribution, this can be really tricky. However, when you integrate this thing, right, if f is a uniform distribution, then this ends up being negative 1 over b minus a, the integral of negative infinity to, of a to b of x squared dx, and that's 1/3 x cubed. So everything becomes much easier with a uniform distribution, and you can have much more complicated utility functions, and thereby the uniform distribution is incredibly useful for trying to deal with uncertainty in game theory when you want an actual analytic closed form answer and not a bunch of messy numerical answers, because it actually produces a closed form analytic answer. In this case, you would have 1/3 b cubed minus a cubed all over b minus a, and there we go. That would be the actual answer. I will see a couple more examples in the next module, but that's the point. That's why it's so used so often in using game theory. Before finishing this, I just want to talk briefly about one more small topic, and that is iterated expectations. Now, in the previous module, we discussed joint distributions a little bit, well, a whole lot, I guess. That's going to be related to the idea of iterated expectations. An iterated expectation is when you have two different variables. You have the expectation of one given a second one, right? And you want to basically remove the dependence on the second one. And it turns out the law is this, and we'll go through and show how it works in a second. The unconditional expectation of x over x is equal to the expectation over y of the conditional expectation of x given y of x given y. So if you have some conditional expectation of x given some y, then you take the expected value of that thing, of that conditional expectation, you basically average out all the y and just now have the expectation over x by itself. This is the law of iterated expectations, and it's useful in some contexts in game theory. You can see how this works using the discrete case that are easier than the continuous case. Although both work. So let's start off on the right there. This is going to equal the expectation over y of the sum on x of x, little x, times the probability that big X equals little x, given big Y equals some little y. That's going to equal the sum on x of x, the sum on y, sorry, out front, of the sum of x and x, probability that big X equals little x times big Y equals little y, times the probability that big Y equals little y. Okay. So we're using definitions of the expected values to do this. Well, let's change the order of the sums here. You get big X, you get sum over x of little x times sum over y times the probability of this. This thing, however, is the conditional expectation. So this is like the distribute for a discrete case. It's f of x given y, or x given y. And the thing over here is the unconditional, the marginal distribution. And if you recall correctly, and this should be lower cases, if you recall correctly, that thing is equal to the joint distribution of x and y. So therefore this thing is going to be the joint distribution of x and y. If I'm summing over the joint distribution of x and y, just over y with nothing else attached to it, I basically sum out the y's. And I'm left with the unconditional distribution over x, which is just the probability that x equals x independent of y, unconditional on y. Right? Because this thing over here, and again, because this thing, right, is equal by definition to the unconditional distribution over x. That was the definition of the unconditional distribution. So we have this, and that is the expected value over x of x. And that gives the left-hand side up here, and that's a proof of the discrete case. Again, this is useful for sometimes in game theory, so it's useful to have this in your back pocket somewhere, although it doesn't come up a ton. Okay. So that's the end of this module. In the next module, we're going to discuss moments of continuous distributions. And again, most of that stuff will be an exact analog to what we did in the previous lecture when we discussed moments. Thank you very much.